Now I would like to invite Adam Marcel to present his paper, a study on failure of double-layer thermal barrier coatings subjected to uniaxial compression test using acoustic emission analysis and digital image correlation. Please, Mr. Adam.
Thank you, Mr. Chairman, for the kind introduction. Ladies and gentlemen, thanks for having me here. My name is Marcel Adam. I'm a PhD student at the Technical University of Darmstadt, and my talk today is about the failure behavior of modern double-layer thermal barrier coatings. So, this is outlined. First of all, it might be necessary to introduce you into thermal barrier coatings because I've seen there are only 3 talks about this topic on the conference. So that's the first one. We had to look at it. And after that, we have a short look at the experimental data assessment we use for our studies, followed by some results and the analysis of damage mechanisms in those double-layer coating systems. And I will close the talk with a summary and an outlook. So, to protect gas turbine components, for example, turbine vanes and blades or heat shield from the impact of high temperature, which is produced from gases coming from the combustion chamber, we already use some kind of thermal barrier coating systems. And we have a substrate which is normally made out of nickel or cobalt-based superalloy, which gives us the geometry and the structural integrity of our gas turbine components. On top of that, we will find a bond coat layer, which is normally made from metal. Metal is the meaning for cobalt or nickel or composition of that, chrome, aluminum, and yttria alloy, which provides adhesion between the ceramic coating and the substrate. And on top of that, we will find a ceramic coating normally made from yttria stabilized zirconia or YZ. This provides the thermal insulation. We need thermal insulation, we need a ceramic coating with a low conductivity to decrease the temperature on the surface from nearly 1,200 degrees Celsius to 950 degrees Celsius on the ceramic bond coat interface. Here on the right side, on the left side, we see a typical picture of a ceramic coating produced by an atmospheric plasma spray. So this system is called conventional single-layer TBC. Having a look at the history of high-temperature materials, and we clearly see those single-layer thermal barrier coatings have been used since nearly 30 years. And since that time, we are limited to maximum material temperatures of about 1,200 degrees Celsius. But the gas turbine industry requests for more efficient gas turbines, and more efficient gas turbine means we have to produce thermal barrier coatings which can resist temperatures maybe up to 1,500 degrees, for example. And to get this point, we made an APS sprayed, atmospheric plasma sprayed double-layer coating consisting of a conventional system, and on top of that we had an additional layer made from gadolinium zirconate. And gadolinium zirconate is predicted to withstand temperatures up to 1,500, maybe 1,530 degrees Celsius. So that's the double-layer thermal barrier coatings we talk about on the next slides. And in thermal barrier coatings, you will often find very different failure mechanisms. For example, we will find an interface with a cracked row, or you will find some kind of buckling or escalation. And if you want to study your surface area coding and assess the lifetime of your surface area coding, then you have to take all these failure mechanisms into account. And in the past, researchers developed several lifetime models to do that. And in the literature, you will find empirical, phenomenological ones, models which were based on TGO grow and so on. But in case of double-layer surface area coatings, they all won't work. So in our studies, we use the mechanism-based model, which is mainly based on the Griffith criterion to describe the failure of brittle materials, and has been modified a little bit to get these critical strain as a parameter which describes the lifetime. It wasn't modified by us, but by colleagues from the Forschung Institute in Frankfurt, and I think they did it 10 years ago. Yeah. And that's the main parameter we use to assess the lifetime of our double-layer coatings in the next slides. Yeah. So for the experimental data assessment, we are not only interested in having this critical strain or lifetime of double-layer surface area coatings, we are also interested in having an information how a change in this interface geometry, interface curvature, acts on the lifetime of our double-layer coatings. And we are also interested in having an information about how the thermal pre-aging process acts on the lifetime. So that's why we used those kinds of pins. We segmentally coated with YZ and gadolinium zirbinate by an APS process, and we cutted our pins into cylindrical specimens by water jet cutting. And prior to our mechanical tests, we performed some isothermal and cyclic oxidation tests between room temperature and 1050 degrees Celsius and up to 1500 hours or 500 cycles. That's the experimental setup we used. It's mainly based on a conventional compression test setup. We perform compression tests in addition to national standards, measure the axial or longitudinal deformation of our cylindrical specimens, and we additionally equipped our test rig with acoustic emission measurement equipment. Additional to that, we also used stereo camera setup. So we had two CMOS cameras in stereo camera setup with oriented with a certain angle of 25 degrees to each other to have a look at the two-dimensional surface strain field on a curved TBC surface. And with this stereo camera setup, we also get the information about the radial or out-of-plane deformation of our cylindrical samples. So let's have a look at the results we got from the acoustic emission analysis. Here's a typical plot seen for the APS grade double-layer coating, pre-aged between room temperature and 1050 degrees Celsius up to 500 cycles. And we have on the vertical axis the acoustic emission energy, on the horizontal axis the global measured global strain, and here's another secondary vertical axis, which is the external load we applied onto our cylindrical specimens. And as you can see here, if we apply a load, there is a long range where nothing happens. This can be clearly seen in the low level of the acoustic emission energy signals we got from the TBC. And reaching a certain point of external load, there is an exponential rising acoustic emission energy. At this point, we define this point as the critical point where the TBC is going to fail. Yeah? And this point is used, from this point we measure the global strain, and we define this point as a global failure strain of our thermal barrier coating. And in that example, we get a global failure strain of about 0.9%. Having a look at all the systems or all the specimens we tested and all the pre-aging conditions we tested, and also the types of specimens we tested, then we get an information about the effect of the interface curvature on the TBC lifetime on the double layer system. Yeah? So first of all, we see here the failure strain, and here we have different types of pre-oxidation conditions. So first of all, we have a look at the no pre-age or S-grade conditions, and we clearly see for the small specimens here, there is a gap between small and large specimens. So this means we have found a lower strain tolerance of our double layer coatings with stronger interface curvature. Yeah? If this curvature here is stronger, which is in the case of a small specimen, then the strain tolerance is much lower than in the case of a smooth curvature. Yeah. And we also find, having looked at the data, we also find a significant decrease due to the thermal pre-aging. And what we see is that the thermal aging or the thermal cyclic agent leads to a more extensive degradation of our double layer coating system. And to conclude this slide, all results are in good agreement to previous studies on single layer coatings. From the acoustic emission measurements, we get only the information about when our TBC is going to fail, but we have no information about how does it fail. Yeah? And this information we get from the correlation between the acoustic emission and the digital image correlation measurements. So again, here is the acoustic emission energy over a global strain measured for the double layer coating system, which we have seen before. And I marked 4 specific points in the acoustic emission signals. So they belong to different load levels. At point number 1, load level number 1, this is the stage directly after preload. We have a uniform global displacement. Here, this I should mention this. We see the out-of-plane deformation, which means the radial deformation of our specimens. So here in the load level number 1, we have a uniform global out-of-plane deformation, and if we increase the load and go into the load level number 2, which is the load level directly after TBC is going to fail, then we clearly see this local narrow areas of intense out-of-plane deformation. We can call it red spots maybe. And these spots were belong to a partially buckling of our gadolinium zirconate layer. So the YZ layer is intact, but only the gadolinium zircon layer is going to fail. Yeah. And with a further increase in the load, these red spots are going to increase of size and intensity, and the gadolinium zirconate buckling would be much more here. Again, having a little closer look at the load level number 2, note it was the state directly after TBC damage occurs, we can evaluate our out-of-plane deformation along one line. It's called the line of sight, which corresponds to the focus line of our cameras we used in a digital image correlation. And note these red spots, and they fit to the peaks in the out-of-plane deformation graph. But also note the gap between the top edge out-of-plane deformation and the bottom edge out-of-plane deformation, which means here and here. And this gap is, it's a local delamination or interfacial crack growth within our coding, starting from the top edge. Last but not least, at load level number 4, it was the load level where the highest acoustic emission energy level has been reached. And we clearly see here we have the original image and the EIC evaluated image, also the out-of-plane deformation, and we clearly see this crack path in the original image. We can see the crack path here, very good in the EIC image, and as mentioned before, we have these red spots of gadolinium zirconate buckling, and also we see the widespread area of interfacial crack growth or delamination starting from the top edge. So let's come to the summary and an outlook I will give you. I introduced you to the concept of double-layer thermal barrier coatings to withstand higher temperatures and to increase the gas turbine efficiency as well. And we found an influence of the geometric boundary conditions on the lifetime of those double-layer coatings, and we found that a stronger interface leads to lower critical strain values, so you have a lower strain tolerance. And we also found by studying the acoustic emission measurements together with digital image correlation, we found different mechanisms in those double-layer coatings, and the double-layer coatings started to fail by gadolinium zirconate buckling. For further investigations, we wanted to have a closer look on the role of the substrate anisotropy on the gadolinium zirconate buckling process, and after that we want to transfer our experiments and results to real component shapes, for example those gas turbine late light specimens. Some acknowledgements, and thanks for your attention.
Thank you, Mr. Adam, for your nice presentation.